This differential equation, equation 2214 in your textbook, is called the Hermite equation. It's a second order differential equation, and it's a differential equation that comes up in quantum mechanics problems when you're trying to solve the one-dimensional harmonic oscillator problems for energy and wave functions. Okay, so the solutions to this differential equation, okay, this is called Hermite equation. The solution to this differential equations, okay, or the solutions, they are polynomial solutions, and they are known as Hermite functions, Hn of x. So this Hn of x refers to those solutions for this differential equation down here, and those Hermite solutions or Hermite functions, Hn of x, just like Legendre polynomials and other functions, they are orthogonal on minus infinity to plus infinity. Okay, with respect they're orthogonal in general, and now I'm gonna prove in this question that they are orthogonal with respect to the weight function e to the minus x squared. Okay, and so the way I'm gonna do this, first I'm gonna rewrite this differential equation. Okay, now noticing that if I were to take the derivative, okay, d over dx of y prime, okay, times e to the minus x squared, right? What do I get here? Well, I get let's go ahead and differentiate it. So this is the product rule, so this would be y double prime times the second as is, okay, plus, now if I bring this down, so this is going to be y prime, and then e to the minus x squared, and then chain rule, this would be minus 2x, so this would become here minus 2x. Okay, now notice if I factor e to the minus x squared from both of these, I get y double prime minus 2xy prime, which is similar to what I have here, right? The first two components, except that this is multiplied by e to the minus x squared. So to alleviate the effect of this, what I could do, I could simply, if I multiply this equation here by e to the x squared, let's do it on the right hand side. Okay, so in effect I would have multiplied this by e to the x squared, and what that does, it would cancel the effect of this, because you get e to the 0, which is 1, and I get exactly this part of the differential equation. Okay, so in other words, what I've proved now is that e to the x squared times d over dx y prime e to the minus x squared, after I FOIL this with the product rule and cancel the effect of e to the minus x squared by e to the x squared, I do indeed get y double prime minus 2xy prime, and as a result I will replace y double prime minus 2xy prime with the left hand side of this blue equation in my original Hermite equation. So plug this in 2214, and when I do that, I will get d over dx, or first let's write e to the x squared, d over dx of y prime e to the minus x squared plus 2ny equals 0. Okay, okay, so now assuming that the Hermite polynomials are my solutions for this differential equation, so the Hermite polynomials are, let's call one of them hnx and hmx, and so those are the solutions for my differential equations. Those are my y's. So the differential equation would have to satisfy each one of these. So now I'm gonna plug these here, both in the differential equation, and I will get e to the x squared, or instead of y prime now, this will be h prime n. So e to the minus x squared times h prime n x plus 2n h n x equals 0. Likewise for hm. Notice when I use hn, the n is the integer for the polynomials. When I use m, I change n to m. Okay, so this is equal 0. Okay, and now the trick is to actually multiply the first one by hm and the second one by hn. Okay, so I'm gonna multiply this whole equation here by hm of x, and I'm gonna multiply this here by hn of x, and so the first equation becomes e to the x squared hm. The right hand side does not change because there's 0 there. And now I'm gonna subtract these two equations from each other. So subtract, and I'm gonna simplify the algebra as well. So from here, when I subtract, I'm gonna have e to the x squared, common factor, right? So I will get e to the x squared times hm minus plus 2, factor out the 2, I get n minus m. These two terms are the same thing, so factor out 2 and hn hm equals 0. Okay. Now 1 second here, I need to close a bracket here because e to the x squared does not multiply the other term, correct? Okay, so now okay, notice one thing here. If I apply the product rule backwards on this, okay, you recognize that this is actually the derivative. But before I do that, I want to do a quick, actually we'll take care of that later. Okay, so let's do that. So then I will get e to the x squared, and then I will have here hm d over dx e minus x squared h prime n plus, so now this is the added term, plus e to the minus x squared h prime n. Okay, back to the second term. So let me get back to the previous color, minus hn d over dx e to the minus x squared h prime m. Okay, and now I'm gonna subtract that same term. I could do that, it's if I hadn't done anything really. H prime n h prime m plus the last term, which has nothing to do with this. This is outside the bracket, so plus 2 n minus m hn hm equals 0. Okay, so let me justify what I did. The reason I added and subtracted these two terms is because if you look now at these two highlighted terms, they're the product rule. Because if I were to differentiate, so I could rewrite those couple of terms taking the product rule backwards. I could say this is the same thing as d over dx, right, of e to the minus x squared, okay, times h m h prime n, right? Let me see, h m, so this is e to the h prime m, sorry. So this is the product rule for that. Okay, so this would be yeah, sorry, no, hm here. Okay, in other words, we could group this h prime n with e to the minus x squared. So it's like considering this as 1, so the derivative of this times hm as is, plus the derivative h prime m times the derivative of the first. In other words, maybe this is sounding a little bit confusing, but what I'm trying to say is if I were, let me go to that step directly, and then it'll become clear what I'm doing. This OneNote is giving me some hard time. So slow. Okay, here's what I'm trying to say. If I were to rewrite the above green expression, or the expression where I added and subtracted those two terms, I could now rewrite it as d over dx of, there's an e to the x squared outside. Okay, this doesn't change. D over dx of e to the minus x squared. Okay, h m h prime n okay, so this is all the derivative minus d over dx of e to the minus x squared hn h prime m. Okay, plus, so let's put a bracket on this, plus the last term hn h. Okay, so here's what I'm trying to say. If you were to FOIL the product rule on this, okay, you will get h. So what I'm trying to do is group these two together, so you would get exactly these two, right? So you would get e to the derivative of e to the minus x squared h prime of n times hm, okay, plus now e to the minus x squared h prime n as is times the derivative of hm, which is h prime m, and that would get you this term here. And then if you apply the derivative on the second term, e to the minus x squared hn h prime m, by the same exact product rule, you would get exactly these two. So I just put together those four terms using the product rule backwards into two derivatives. Okay, and now by doing that, what I could do is I could, since derivatives are distributed over addition, I could say this is the same thing as derivative e to the minus x squared common factor hm h prime n minus hn h prime m. Okay, and I can close this, plus 2n minus m hn hm equals 0. And now what I want to do, okay, I want to get rid of this guy here, so I'm gonna divide e to the minus x, e to the x squared. So if I divide this whole equation by e to the x squared, I will get, so divide by e to the x squared. So I'm trying to leave the derivative by itself so I can actually integrate. So this one here goes away, and I get e to the minus x squared hm h prime n minus hn h prime m plus 2 n minus m. Now I divided by e to the x squared, or multiply by e to the minus x squared, either way, so we get e to the minus x squared here, hn hm. equals 0. Okay, and now I'm just going to integrate this equation from minus infinity to plus infinity, right? Wait, I forgot d over dx here. Yeah, there's a d over dx here of this. Okay, so integrate from minus infinity to plus infinity. And as you know from fundamental theorem of calculus, once I do, let me show you so I can skip a step here. If I were, so I could multiply this dx over here, the whole equation by dx, right? So let me first do that actually. So I would get the derivative of e to the minus x squared h prime n h prime m plus 2n minus m e to the minus x squared hn hm dx equals 0. And as you know from fundamental theorem of calculus, once I integrate a d something, right, the antiderivative of the derivative gets you that something, as long as it's the same variable, and it is. So once I'm integrating here from minus infinity to plus infinity. So once I put an integral here and an integral here, those are constants. I can pull them outside the integral. From minus infinity to plus infinity, minus infinity to plus infinity. On the first term, I have e to the minus x squared hm h prime n minus hn h prime m, right? And this is evaluated from minus infinity to plus infinity. However, as you know, the limit of e to the minus x squared, whether x goes to plus infinity or minus infinity, this guy dies down. The answer is 0. So this whole term drops out to 0, which means the remaining term here has to equal 0, right? So that means, back to the original question, so that means 2 n minus m from minus infinity to plus infinity e to the minus x squared hn hm dx. And again, keep in mind those are both functions of x, equals 0. So either n equals m, then they may not be orthogonal if they're the same function, but that's not what I'm interested in. I'm interested in this guy, or the integral from minus infinity to plus infinity e to the minus x squared hn hm dx equals 0, and hence they are orthogonal. Therefore functions are orthogonal over the weighted function e to the minus x squared. And this would be the result of this proof. This concludes the proof that the Hermite polynomials are indeed orthogonal.